Hello, Chem 111. This video is about Lewis structures for molecules that have expanded octets on the central atom. You'll talk in class about why these things happen. Here I'm just going to outline three different examples. And I like to divide these structures into three different types. Number one, ones that are obvious just from the chemical formula, SF6. We all know fluorine has to go on the outside. If you're going to have 6 fluorines on the outside of one atom, that atom has to have at least 6 bonds. Number two type is less immediately obvious. So if you look at something like xenon difluoride, it's not obvious that xenon's going to have an expanded octet, but as you start to draw the Lewis structure, you see you really have no choice. And then the final type, number three, it's not obvious at all, but when you draw the Lewis structure without an expanded octet, you see that it has some pretty bad formal charge, and expanding the octet allows the structure to eliminate that. So I want to make a key point to start, which is that only atoms below the first full row of the periodic table can do this. And so I'll just remind you what I mean. The first full row, things that make molecules are here. They can never have an expanded octet. So nitrogen, oxygen, carbon, fluorine, boron can never have an expanded octet. It's the things below them that sometimes do. Okay, so we'll start with SF6 and we'll just draw the Lewis structure. So SF6, the valence electrons, sulfur has 6 valence electrons. It's in oxygen's column. Fluorine has 7 because it's a halogen. And so that gives us 48 valence electrons total. Fluorine is always on the outside. It's the most electronegative element. So sulfur is less electronegative than fluorine. It has to go on the inside. So start my structure this way. And then I have 6 fluorines. They have to be on the outside. So I really have no choice but to put an expanded octet around sulfur. If you accept that SF6, sulfur hexafluoride, is a molecule, and in fact it is, you have to accept that sulfur has an expanded octet. So once I've done that, oops, I have 6 bonds, so I've used up 12 in the skeleton. I have 36 valence electrons left, and you can get very good at drawing dots just with this one structure. I have 36, I have 6 fluorines, so each fluorine gets 6 electrons as its 3 remaining lone pairs. And then we're done. So sulfur has an expanded octet. Fluorine does not have an expanded octet. It cannot. And you can just check the formal charge if you want to, which you probably should. Formal charge of sulfur, it starts with 6 valence electrons. It has 0 electrons in lone pairs. It gets half of the 12 electrons in the bonding pairs, so sulfur has a formal charge of 0. And fluorine, as always here, has a formal charge of 0 as well. It has 6 electrons in lone pairs. It gets half of the 2 in the bond, each fluorine. So fluorine also has a 0 formal charge, and that is the structure of SF6. So I call that obvious because as soon as you start to draw the skeleton, you see I have to put 6 atoms around my central atom. Okay. The next one is xenon difluoride, XeF2. Okay, so the valence electrons here, xenon is a noble gas. It has 8 valence electrons. Fluorine has 7. Just like to label those so I know I've done my work. And so we have 14 plus 8, or 22 valence electrons. Okay, so again, the structure, we don't have a lot of choice on the structure. Fluorine has to go on the outside, so I'll draw it like that. I've used up 4 electrons in my skeleton, so I have 18 electrons left. Okay, so I start by distributing them on the outer atoms. I can put 6 on each fluorine to get them to an octet, so I've used up 12. I now have 6 valence electrons left, and the only place they can go is xenon. Fluorine can't have an expanded octet, it's full. So I have 2, 4, 6 on xenon. And that's typically how we draw the Lewis structure. We just start packing lone pairs around the central atom like that. And that's the structure. So we can, again, check the formal charge. The formal charge of xenon is, it has 8 valence electrons. We subtract off, it has 6 electrons in lone pairs. It gets half of the 4 electrons it has in bonds. So xenon has a formal charge of 0. And again, fluorine, it's just like the fluorines above. It's like all fluorines, it always does the same thing, has a formal charge of 0 as well. So that molecule's happy from a formal charge standpoint. As long as you accept that this molecule exists, and it does, that really has to be the structure. Note that you can't make a double bond between xenon and fluorine with one of those lone pairs because that would give fluorine an expanded octet. Fluorine's a first row element, can never have an expanded octet. Okay, so things like xenon difluoride, you don't find out it has an expanded octet until you draw the Lewis structure. But once you start drawing, you don't really have a choice. The final type, and chlorate, ClO3- is an example of this, is a little different. Okay, so the valence electrons here, chlorine has 7, and each oxygen atom has 6. And it's -1, so we have to add an extra electron. So we get 18 plus 7 is 25, plus 1 is 26. So we have 26 valence electrons. The structure on this is one of those cases where you might actually have to look up electronegativity to see that chlorine is less electronegative and goes in the center. It's also, this is an oxoanion. I'll just write that down. It's a nice fact. Oxoanion, meaning a polyatomic anion where there's a central atom surrounded by oxygens. There are a lot of these: sulfate, chlorate, nitrate, bromate, etc., etc. All right, so we'll start with our chlorine there and put our 3 oxygens around it. I have used 6 electrons in the skeleton, so I am left with 20. I can put 6 on each of my 3 oxygens to satisfy their octet, and that uses up 18 of the 20 valence electrons I have left, and I have 2 more. And that's my initial structure. And everything here has an octet. So great. Let's check the formal charge. The formal charge on the chlorine, it starts with 7 valence electrons here. We subtract off the 2 that are in the lone pair, and it gets 1/2 of those 6 electrons in bonding pairs. So chlorine, has a formal charge of +2. Oxygen, each oxygen in this structure is the same, has a formal charge, just has 6 valence electrons. Each oxygen has 6 electrons in lone pairs, plus each oxygen gets half of its bonding pair, so each oxygen here is -1. So if I'm going to complete this structure, I have to show all my formal charges. Now, I said previously, at least in my class, and probably your professors did too, so problems. So first of all, a formal charge of +2 is excessive, really not very stable. And we have what I would call a necessary formal charge. We have 3 -1s canceling out the +2. I'm skipping my book group to do this video. All right. So every atom has a formal charge. And, sometimes that happens in a molecule. Every atom has a non-zero formal charge. But if there's a way out of it, that's not a very stable situation. And there is a way out of this. the way out of this, the solution, because chlorine is not in the first row, it's in the second full row. So the solution is to expand the octet on the central atom. Note that oxygen cannot have an expanded octet. It's in the first row. Expand the octet on the central atom until its formal charge is 0. So chlorine right now has +2. So that means it's going to, we're going to have to give it 2 more bonds. We can't give it more lone pairs really because oxygen needs to see all the electrons it sees. So we're going to need 2 bonding pairs to bring that formal charge down. So I'll start with these electrons and these electrons. And I will just show the structure down here. So if I do that, I get ClO. This one stayed as a single bond, and the lone pair stays on the chlorine. The 2 oxygens with the double bonds have 2 lone pairs, and this one stays with the 3 lone pairs. So this oxygen still has a -1 formal charge. It looks just like it did in the other structure. The formal charge of the oxygens with the double bond is, I don't know why I wrote equals twice. Oh, I do, because 1 isn't an equals, it's a double bond. All right. And you might recognize this already. Oxygen with 2 bonds has a formal charge of 0. So it has 6 valence electrons, 4 electrons in lone pairs. It gets half of the 4 electrons in the bonding pair. So those oxygens have a 0 formal charge. And the chlorine in this structure, again, starts with 7, still has 2 electrons in lone pairs, but it now has, it gets 1/2, it has 5 bonds, right? 2 double bonds and a single bond. So it gets half of those 10 electrons, and that chlorine now has a formal charge of 0. So I did what I said I would do. I expanded the octet on the central atom until its formal charge is 0. Now, if you're paying attention, you notice that I had a choice about where I drew those double bonds from. And when I have a choice, that means I have resonance structure. So we can think of this as moving the single bond around the molecule. So I'll do this, and now I'm going to draw a resonance arrow to indicate that I'm drawing resonance structures. So I can draw this resonance structure here. Make sure I put all the lone pairs where they belong. Especially important to remember that lone pair on the chlorine. I personally have a problem and sometimes forget that. This oxygen is now the one with the negative formal charge because it has the single bond. And then we have one more movement we can do. We can make this one back into a double bond and turn this into a single bond. And so my third resonance structure is this. With a negative charge. And so if I were showing this as my answer, I would make sure to box together these 3 resonance structures. Together make up the best structure for chlorate. So a few final points on this particular structure. Final points. So one, I just want to reiterate, is we expanded the octet until the formal charge of chlorine was 0. We could draw a series of structures that actually stopped short of that, right? So we could do 1 double bond. If we do this, and this is just one of the structures, right? We would have, I'm not going to do this out. You can prove that this is true. You have a plus on the chlorine. So it started at +2. We could make 1 double bond and bring it down to +1 and have 2 oxygens with negative charge, etc., because that also has 2 other resonance structures. But this is not as good as my final answer. So at least in my universe, you don't need to show this intermediate option because it's not as good as the example where you take the chlorine all the way to formal charge of 0. So that's one final point. My other point is that not only did we eliminate the formal charge on chlorine and reduce the number of oxygen atoms that have formal charge, but now, because of resonance, the one negative formal charge in this molecule is shared between all three oxygen atoms. Um, and that is favorable always. Not only did we eliminate and reduce, but the formal charge of -1 is now shared by all three oxygen atoms, which is more favorable. More favorable than what? More favorable than being sequestered, to use a fancy word that just came to me, on one atom. So this is not just a good Lewis structure, it's a great Lewis structure. It has the minimal amount of formal charge. This is a molecule that has a -1 overall charge, so someone's got to have a -1 formal charge. So we minimized it and we made it shared between three oxygen atoms. Okay. So as you can see, this conceptually is a little more complicated than the other two types, but you will see this type of structure. I'll tell you now, you'll see it in a lot of oxo anions. When you can expand the formal charge, and make sure you can, i.e. don't do this for molecules with first row atoms only, but this does make more stable molecules.